So something I presented in one of the first shows for rotational motion was a GIF that had two objects rolling. They looked exactly the same, and one rolled down faster than the other. And here on the left, we have another animation showing exactly what would happen if I raced different types of objects down a ramp. And the most surprising thing that I remember seeing when I first looked at it was that a sliding object actually beats things that are rolling, and I wouldn't have predicted that at all. I would have thought that a rolling object is going to roll down faster. Another observation I would have made is I probably would have said that this hoop would have gone down faster because it has less mass than these solid cylinders, but it actually is the slowest. So there's some really strange things happening over there, and for people that are studying rotational dynamics, this is probably the weirdest demonstration that they usually see. So the topic that we're going to use to explain that is the importance of rotational kinetic energy. All right, so all that gravitational potential energy that these objects would have at the top is going to be distributed. For the sliding object, that gravitational potential energy just goes into the movement of a point mass, into kinetic energy. There's no energy that is going to have to go into the inertial change of rotation. So it slides down. Now the only place that it would lose energy would be due to friction. But let's just assume that that's minimal. It's there, but it's minimal. Okay? And all these other guys, well, they all have different inertias, and that would explain why some would have to use a little bit more work to get them rolling than others. And that's the simple conceptual explanation as to what we're seeing. The hoop, surprisingly, has the greatest inertial change. Okay? All right, so let's take a look at how we can derive an equation for calculating rotational kinetic energy. All right, so the standard formula for kinetic energy of a system is equal to 1/2 mv squared. Now for rotational kinetic energy, we don't have a mass, we have an inertial mass. All right, so for the kinetic energy of something that's rotating, another way of describing mv squared, I can say it in another way, that the sum of a rotating kinetic energy of a rotating object is equal to 1/2 mr squared times omega squared. Okay, and the point being there is that omega times r is velocity. All right, so the angular speed times r is equal to velocity. So if I know that, and I plug that into there, that is the same as saying 1/2 mv squared. Okay, and what else is interesting from this derivation is that mr squared is our typical inertial mass of an object. Okay, and then all these little coefficients in the front depend on the shape of the object, but the simplest one I ever presented to you, mr squared, okay, would be the inertial mass of one particular object. You can go back to that picture I said in the first video to find out which equation that corresponds to. So I can say that 1/2 times the sum of mr squared, which is my inertial mass, times omega squared is equal to rotational kinetic energy. That's how much energy of rotation. Okay, so for example, if I had a pulley attached to a wall, okay, that pulley, as that pulley is spinning, it would have zero translational kinetic energy. It's not going anywhere. So its kinetic energy in translation is going to be zero. But it has kinetic energy. It's rotating. It has rotational kinetic energy. Okay, so there's a difference between translational kinetic energy, which is your standard moving from point A to point B, and then there's rotational energy associated with rotating about an axis of rotation. Okay, and that formula here describes that. So 1/2 times the inertia of an object, depending on its shape, it has a different formula for that, times the angular frequency squared. All right, that's the important part of today's lesson. All right, so let's go take a look at an object. Okay, so let's say that we have, an object such as a sphere. Okay, this is like a bowling ball. Okay, and the bowling ball is going down a ramp, and let's say this ramp is a 30-degree inclination, and let's say it's 10 meters high. Okay, the question that I want to ask is, what is the velocity, okay, the linear velocity of the ball at the bottom of the ramp? Okay, how can we figure that out? So in standard form, if it wasn't rolling, if it was just sliding, we would just say mgh is equal to 1/2 mv squared, and then we'd be able to solve for the square root of 2gh is equal to velocity. And if we did that, we would calculate a velocity that is going to be much higher than what the ball actually is. That would be just for the sliding object. That's assuming that there's minimal friction. Okay, so what do we have to do? So we're going to get rid of this. So again, mgh, which is my gravitational potential energy, is going to be converted into kinetic energy. It's going to be converted into two forms. It's going to be converted into our standard 1/2 mv squared, like I just described, and then it's going to be converted into 1/2 times my inertial mass of that bowling ball times the angular frequency of that bowling ball, okay, squared. All right, so off we go. Let's continue with this. So let's just assume that we're not going to actually calculate a final number because I didn't give you the mass of the bowling ball, but we're going to come up with a relationship for this. So mgh is equal to 1/2 mv squared plus 1/2. Now, if I went back to that picture I showed you in one of the videos to find out what the inertial mass is of a sphere, you would find out that the formula looks like this. 2/5 times the mass of that bowling ball times r squared. So you would need to know the radius of that bowling ball times my angular frequency squared. Now, since I'm trying to find the velocity, I can convert angular frequency from my linear velocity by that relationship and square it. Okay, so right now what I'm trying to do is I'm trying to derive an equation for the velocity. All right, so I can see that I can cancel my m's throughout this entire relationship. Is there anything else that I can do? Probably, but let's just continue. All right, so now I got gh is equal to 1/2 v squared plus 2/10, okay, like multiply those fractions together, times v squared times r, I believe, if my math is correct. Let's just double check that. No, that was wrong again. Okay, so I forgot to square that, so my r cancels out. Oh, that's pretty cool. All right, so my r cancels out. I don't even need to know the radius. Now that's an interesting situation. If the r canceled out, that means that the radius doesn't matter. If I had a 5-meter radius or a 1-meter radius, it would factor out, so that both of those bowling balls, as long as they're the same material, okay, and as long as they have the same shape, they would come down at the exact same speed. Oh man. All right, so then we're left with gh is equal to 7/10 v squared, okay, and then if I multiply this by over, wow, okay, I'm actually saying wow because this is actually pretty cool. Okay, so this is an interesting relationship where we're able to calculate the velocity, and it doesn't depend anything on the radius, it doesn't depend on the mass, it depends on the shape of the ball. All right, so if I had two bowling balls of different size, they would actually roll down at the exact same speed as long as they had the same material and the same shape. Okay, and this is how we derive the formula that 10/7 times gh square rooted is going to be equal to my velocity.